Okay, so we have another question for you related to geometrical isomerism. Question number 7, we need to find out the compound out of the 4 options given which exhibits geometrical isomerism. One difference which you will see is a new ligand group which we have introduced in this question, and also the central metal atom in this case is platinum. So let's see how we'll approach.
So in this is a multiple choice question, so we could have multiple option answers for this which are correct. So let's check the first option. The first option will have a platinum with ethylene diamine. You know that it is a bidentate ligand, so it will have 2 donation points.
Okay.
And so this does not have any possibility of having a so it could not have geometrical isomers. As you can see that there's no unique configurations we can draw.
Okay.
This is the A option. The B option has again the same issue that you cannot make any unique configurations for this case. The C option, you can, as you can see, you have 2 Cl groups and 2 En groups. So in this case,
Okay.
you could have it this way. This is an octahedral. The earlier 2 were square planar. So you could have this configuration, or you can
Okay.
have a trans sort of a configuration where you have a Cl up and a Cl below the plane.
Cl on opposite sides. Of
Yeah,
each other.
opposite sides of the plane, and you have 2 ethylene diamine groups on the plane. So you have this is one answer. So C we know as an answer. Now we
Okay.
can check the D option. D option is a very simple case of an example which is always considered. So you can just straight away see that this is your trans isomer and this is your cis isomer. So the answers are C and D for this case.
So this was a fairly simple question just to brush up your knowledge on geometrical isomerism. Only thing was we introduced a new ligand group, ethylene group, which is a bidentate ligand. So you need to take into account as well when you're drawing the structures of the coordination compounds. So we have talked about geometrical isomerism in the previous 2 problems. Now we'll move to ionization isomers. We are asked to find the ionization isomer of the coordination compound whose chemical formula is shown. So out of the 4 options, we need to select the correct ionization isomer.
So in this particular question, we'll have to check each option which is an ionization isomer or not. So A option gives out Cl and a particular we'll get Cl minus as an ion and a particular coordination entity as an ion. So this you can see that it's the same on ionizing it, and the medium you get the same particular ion. In the
Okay.
B option you get NO2 minus. So this is one ionization isomer because this gives you another ion, a different ionization product when you ionize the particular compound. C option is a linkage isomer because you can see that instead of NO2 this is ONO. This is a nitrito O. And the D option is a solvate isomer. It is a solvate isomerism example. So as you can see, B is the correct answer for this case.
So in this question, we see like when the compound will be placed in a polarizable solvent like water, the original compound which is given to us will give chloride ion. So we need to see from all the options what all ions will be received when the compound is placed in water or a polarizable solvent. And in the B part, we'll be getting nitrite ion. So this would be the correct answer. And in the C part, as we see, it's not a ionization isomer since the oxygen atom is donating, while in case of the original compound, the nitrogen atom is acting as the donating ligand group. So it is exhibiting linkage isomerism. Now let's cover a small numerical problem which is often asked in your JEE mains exam. It's the question number 9 says the complex showing a spin only magnetic moment of 2.82 Bohr magneton is. So let's see how to find out the magnetic moment of any coordination compound which is given to us.
So we know that the formula to calculate the spin only magnetic moment is root n into n plus 2. N plus 2 into n is your answer. So this is 2.82.
What is n in this case?
N is the number of unpaired electrons in each metal frame orbital.
Okay.
So unpaired electrons. So in this case we have n into n plus 2 is equal to 8. 2.82 square is 8.
Okay.
And then we can say that n has to be equal to 2 because 2 into 4 is 8. So we know that we have to find the metal which has 2 unpaired electrons out of these options.
Okay.
So we can see the first particular option which is given, that is Ni0. The A option is Ni0, which has to have a D8 and 4s2, 3D8 and 4s2.
Okay.
But it has a strong field ligand, so it will have to have a 3D10 from. It has a very strong field ligand that it has CO group attached to it, so it will have to have 3D10 and it has 0 unpaired electrons. So this is not the answer. We can check the B option, which is Ni2 plus with a weak field ligand attached to it. So it will have a 3D8 in this case. So 3D8 is this configuration in which we have 2 unpaired electrons. So this has to be our answer. But we can still check the other options.
Okay.
So C option has a strong field ligand and it is Ni0. So this will have pairing again. So we will not have any unpaired electrons in this case. So this will be your 3D8 and your 4s2. In the fourth option we have, so this will again not be the answer.
Okay.
And the fourth option has Ni2 plus, which is what we checked over here. But in this case we have a strong field ligand. Cn is a strong field ligand. So we will have pairing in this case, and this will be the configuration we shall get. So it will again have n is equal to 0. So this is also not the answer. So the correct answer is B.
So again, as you saw, this is a very simple question based on a formula used for calculating the magnetic moment. Again, you need to consider the relative strength of the ligands into account while deciding on the number of unpaired electrons. Then you can directly put that into the formula and calculate the magnetic moment. Okay, now let's move to question number 10. In this question, we need to find out the geometrical shape of the complexes which are formed as a result of the reaction of Na2 plus with chloride ion, cyanide ion and water. So let's see, like it's a reaction based question, so let's see how the complexes are actually formed and how we can judge what shape they'll acquire.
So in this case, Ni2 plus will form NiCl4 minus with chloride. This is a standard compound that it always forms.
Okay, so we need to remember these compounds which are formed.
So these are standard compounds which are always formed. You'll actually be able to remember it by the end of practice of this chapter. NiCN42 minus is what is formed from reaction with Cn minus.
Okay.
And NiH2O6 is an octahedral compound that will be formed from this reaction. And we'll have 2 plus because it continues to maintain the charge.
Okay.
So now we'll have to check the geometry for each compound. NiCl42 minus is Ni2 plus with a weak field Cl ligand. So it will have no pairing. So we will have 8 d electrons and our S. And this will be 3d8, 4s0 and 4p0.
Right.
So our configuration will be tetrahedral because it is a sp3 hybridization. NiCN42 minus will be the same 3d8, but it will have pairing in this case because we have a strong field ligand. So this will be the configuration that we will get in this case, and hence we have an empty d orbital, we have an empty s electron orbital, and we have empty p electron orbitals. So in this case we will have dsp2. This is a square planar configuration.
Okay.
So this is tetrahedral, this is square planar, and the third case is Ni2 plus with a weak H2O ligand.
Okay.
And it has octahedral obviously because it is sp3d2, because we will have 3d8 over here, and we will have 4s empty and 4p empty, and we will have empty 4d orbitals as well. And in this case this will be the configuration. So we have sp3d2. This is octahedral.
Okay. So this is again a very simple question. It covers your concepts of of hybridization which you would have studied in the chapter on chemical bonding. So on the just by finding out the d orbital configuration of each of the metal atoms, we can find out the hybridization, and we already know the shapes corresponding to the particular hybridization as we have studied in the chapter on chemical bonding. So again, we'll take into account the effects produced by strong field and strong field and weak field ligands on finding the hybridization and the pairing or unpairing of electrons. So now we have a question for you which has been asked in previous year JEE entrance examinations. Question number 11 states that among the following complexes, you need to find out what all are diamagnetic in nature. We have already shown you the approach for some of the compounds which we have discussed earlier. So a set of 6 compounds are given. So we'll revisit that approach once again, and we'll find out what all diamagnetic complexes exist among these.
Okay. So in this case, we'll first write down the d orbital configuration. So this is the order.
It's good if students remember this this d orbital configuration, as it will help in solving most of the problems.
So you know that this is d1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This makes it easier for us later on to come back and just pick up which particular configuration we are considering. So K option has FeCN6, and this is raised to 3 plus. So we know that this is Fe3 plus because this is 3 is equal to x minus 6.
Okay.
Which is minus 3. So we know that this is x is equal to plus 3. So this is Fe3 plus. Fe3 plus is a D5 configuration because it has D6 and 4s2. So it loses 3 electrons to give D5. And now we can find, now we know that this is a strong field ligand which is attached to it. So they will have to be pairing, but then there is still one unpaired electron because it is odd number of electrons.
Okay, so this has paramagnetic in nature.
Exactly. So n is equal to 1, so paramagnetic. Now L is a cobalt group which is raised to 3 plus again because this is CO3 plus.
Okay.
So now we know that this is a D6 configuration with a strong field ligand, and hence they will be pairing. So we will have to have this configuration which is 3d6, and thus there are no unpaired electrons, and this is diamagnetic. The M option has CO3 plus again. So this has a CO3 plus, and oxalate is C2O4 2 minus. So we can, thus we know that this is 3 minus 3 is equal to x minus 6. So we know that this is 3 plus. Also, as we just did, CO3 plus is a D6 configuration. We know that oxalate is a strong field ligand, so we can hence say that they will be pairing.
Okay.
And all 3 orbitals will be full and will be paired up. The 6 electrons will be paired up. So this has to be diamagnetic again. The N option has Ni 2 plus because H2O is not a charged ligand.
Okay.
And H2O is a weak field ligand, and Ni is D8 configuration, 3D8. So we know that they will not be pairing, and we will have this configuration in the end, which is paramagnetic.
Okay.
As we have seen multiple times before. The O option is PT2 plus. So we can say that it is PT2 plus. We know that PT is 4D8 configuration, and with cyanide ligand, which is a strong field ligand, we can say that they will be pairing. So the 4D8 will be paired up, and
okay,
thus it will be a diamagnetic field ligand. The P option, which has Zn H2O6 NO32 plus, will have Zn2 plus.
Okay. ये exception क्यों नहीं होता इसमें?
So this particular option has Zn which is D10, and it is 2 plus as we've just seen because it has NO3 outside the sphere. So we have Zn2 plus and NO3 is minus, and there are 2 of those, so this will be 2 plus. H2O is uncharged, so we can straight away say that it is 2 plus, and because it's a D10, it is completely packed and it is all paired up, so we cannot have any unpaired electrons, and thus this also has to be diamagnetic. So in this particular question, we've actually seen, just revised all the concepts once.
So I guess students will now be clear in solving problems related to the paramagnetism or diamagnetism, and even the shape and geometry of most of the coordination compounds. So we have another question on IUPAC nomenclature for you. There is slight difference in this question as compared to the first question which we did. So we'll let you know, we'll explain you how to name this particular compound.
So this particular question we need to, first of all, as we can just see as soon as we approach this question, we see that cobalt is in the anionic, the metal complex is in the anion this time. So we have COF6 3 minus. So we straight away know that we have to name it as cobaltate.
Okay.
And we can see that it is x minus 6 is equal to minus 3. So this is x is equal to plus 3. So we know that this is a plus 3 oxidation state cobalt. We first name the anion. So anion is potassium. In this case, we have fluoro as our ligand. So we will write as fluoro.
Okay.
And we have hexa because it is 6. So we name it as potassium hexa fluoro cobaltate 3. So this is the name.
So as you have seen, the only difference here was that the coordination sphere in this case was was occupying the position of the anion, and thus we had to replace the name of the metal item. We had to basically change it. If there had been nickel, we would have changed it to nickelate. So there was cobalt. So in case of cobalt, we have written cobaltate. Rest of the rules for writing the nomenclature of coordination compounds remain the same. Now we'll be discussing a couple of questions related to the CFSE field splitting, which is another important concept in this chapter. Question number 13 we have, in which of the following compounds of cobalt will the magnitude of delta O be the highest? So let's see how to deal with such kind of problems.
So this particular question you need to check what are the ligands which are attached to each group and what are the charges on each metal atom. Since the two metal atoms which are considered in this particular question both belong to the same period, same row of the periodic table, it doesn't exactly make that much of a difference in the answer from that point of view. Okay. This has cobalt 3 plus, as we can directly see. NH3 is not charged. This has chromium 3 plus because Cn is minus 1.
Okay.
Oxalate is minus 2, so this is again plus 3 cobalt. This is also plus 3 cobalt since H2O is an uncharged group. Okay. So we can see that the particular factor that the question is trying to focus on is not the charge. Hence, we have to check the strength of ligands. Strength of ligands, we can directly see that Cn is the strongest ligand among all the options. Right. And NH3 is weaker, oxalate is weaker, and H2O is weaker than Cn minus. Cn minus is the strongest field ligand among them. So B is the answer in this case. You have to remember from this question, you have to remember that as the strength of ligand increases, the delta O also increases.
So another question on the same topic. Among the following, we need to find which has higher delta O. 4 pairs of coordination compounds are given to us, and we need to find out among those pairs which one has a higher delta O value than the other one.
So in this particular question, we are able to check each of our concepts. The first option basically talks about the difference in the strength of ligands. So A option has NH3 and Cn on the two particular compounds which are given. Both are 3 plus compounds. So the factor that they're trying to ask us to consider over here is the strength of ligands. So you need to remember that as strength increases, as we did in the last question also, delta O will increase.
Okay.
So this is B. The second option is correct for this case. The second particular compound is higher delta O.
Okay.
For the B option, for the B particular subpart, we can directly see that this question again focuses on which particular out of the two has strength, higher strength of the ligand. So we again know that F is a weak field ligand compared to NH3. NH3 is stronger, so NH3 will be the correct answer.
So again the second option will have a higher delta O value.
Yes. Again, as strength increases, delta O will increase. So B, second compound is the higher delta O option. The C option basically focuses on this charge of the metal atom. Because both the ligands given are the same. Both have H2O. Both the particular compounds given have H2O. But the first one is plus 2 charge, second is plus 3 charge. So we know as the charge on the metal atom increases, the strength of the delta O also increases. The splitting increases. So, charge increases. You need to remember this for later for other questions that delta O increases. So B option is the second one is again the higher delta O. The fourth one is slightly different than the others. The fourth subpart basically discusses on the fourth one has the same charge, it has the same ligand,
Okay.
but it has metals from different periods of the periodic table. As I discussed in the last question, that all the metals then were from the same period. This time they're from different periods of the periodic table. CO is one row below CO. So hence, as we go down the group, CFSE increases.
Okay.
So this is again something you will have to remember as we go down the group. Delta O increases. So in this case, first one is the higher delta O.
Okay, since rhodium is lies below cobalt in the
Yes.
periodic table. So in this question, the important concept to keep in mind is the dependence of delta O or CFSE field splitting energy on the strength of the ligand, on the group, on the elements present in the different groups of the periodic table, and also on the charge on the central metal line. So now we come to the last question from this chapter. This is again a question on nomenclature. We are given in this question we are given the name of the coordination compound. We need to write down the chemical formula for that particular compound. A set of two compounds are given. So let's see how we'll do it. How we'll do that.
So for the A option, we've been given dichloro bis triphenyl phosphane nickel 2+. So we directly know that Ni2+ is present. We know that there is PPH3 twice because we see that there is bis. We see that it is dichloro, so it is Cl2. But now we know that C comes before P, so we'll have to write it in that order. And we know that the metal always comes before in the coordination entity. So NiCl2 PPH3 twice. So this will be the answer. And because it is Cl2 and Ni is 2+ and PPH3 is uncharged, we directly know that this will be an uncharged sphere because uncharged entity because there will be charge balance by itself.
Okay.
So now the B option has again bis dimethyl glycoxymato, which is also written as DMG. We have DMG2 because it's given that it's bis, and nickel 2. So again, DMG is a negatively charged ligand. So we have a charge balance by itself because it is two minus charged ligands and Ni2+. So we'll directly write down Ni DMG2, and this will be the answer.
So as you can see, you can be asked either the chemical formula or the chemical name of the coordination compounds. So with this we come to the end of this chapter. As you have seen, most of the questions are based on discussing the magnetic nature or finding out the geometry and the shape of the coordination compounds. Sometimes questions are also asked on nomenclature and CFSE field splitting theory as well. So it's very important that you are aware about the relative strength of the ligands because that is the ultimate criterion which helps in coming to the solutions of most of these problems.